Hi, in this video, we are going to see how we can fine-tune CodeLlama 7 billion parameters model on Alpaca 20K dataset. Before diving into the Jupyter notebook, let's get to know what is this CodeLlama 7 billion parameter model. So we'll just directly go to the Hugging Face to know more about this model. So as you can see, CodeLlama is a collection of pre-trained and fine-tuned generative text model ranging in scale from 7 billion to 34 billion parameters. In our case, we are going to use this particular model, CodeLlama 7BHF. And they have also defined what are the current model capabilities. So we can do code completion and infilling using the code that is present here, but instruction chat and Python specialist, these two capabilities are not available right now. So in the fine-tuning process, we would be fine-tuning the model so that it can also follow our instruction and generate code for the prompt that user has given. So this was about the model, and also we can check in files and version. So there are different weights of the model which are uploaded. Going back to our Jupyter notebook, so that was about the model that we are going to fine tune. Now coming to the dataset that we are going to use to fine tune this model. So this is the code Alpaca 20K dataset. So it is divided into 18K rows are in training dataset, and rest of the 2K rows are into the testing dataset. So as you can see, there are two columns basically. One is the prompt, another is the completion. So for example, if a user is giving a query, create a Java class which sorts a given array of numbers, and the array is also given, then the completion is the actual code which is required to complete this prompt. So we can also see the other examples here. Use a loop in Java to print out the squares of number from 1 to 10, and it is the code for that. So we are going to use this data set so that our model is able to understand the instruction and also generate the output in this format. So let's get started with the notebook that we have created. So first of all, we are going to install some of the packages that are required to run this notebook. So it installs Accelerate, PEPT, Bits and Byte, Transformer, TRL, and WANDB for the logging. Hugging Face we are using to upload our generated or trained model, and so on. Also, you can see, we are using this WANDB notebook to upload the logs of our model training to WANDB. Next, we are importing different kind of libraries which will be required to train our model. And now comes the part of setting up the model and the dataset. So as you can see, we have specified the model name, which is CodeLlama 7BHF, and the dataset which we are going to download from the Hugging Face, as we have seen, code Alpaca 20K. So here we are setting up the pre-trained model from the Hugging Face, and we have done load in 8-bit equal to true, so it would be 8-bit quantized model. So if you also want to save more memory, we can use the commented code to load the quantized version of the model, and we can save on the GPU memory by that. And here we have set up the tokenizer using this auto tokenizer from pretrained function. After that, we have just printed out the tokenizer to see if everything looks as expected. So before training our model, we would like to see how our pre-trained model is generating the output and in what format. So you can see we have set up a pipeline from the transformer library that we have imported, and then we have defined the sequences, and as the initial starting point, we have given import socket, and we are defining a function ping exponential backoff. So this is the starting point of the code that a pre-trained model would be generating the output for, and as we generate the sequence using this pipeline function, it would generate the rest of the code. And also here we have given the maximum length, defining how many tokens it would generate. And as we can see, once we run this model, it took around 2 minutes to generate the output, and this is the kind of output that we are currently getting from the pre-trained model, which we have not fine-tuned yet. Now comes the dataset setup part. So here we have defined a new function, get preprocessed CMG history, and there is one more function, tokenize add label. So this is to basically tokenize the whole dataset that we have downloaded, which is Alpaca 20K. And also we can see we have defined a function apply prompt template. So basically, when we are preparing dataset, we have to apply this prompt template to make the dataset trainable. So in the next line, we are actually calling this function get preprocessed CMG history, which will load the dataset from the Hugging Face. And also then we are using a map function to apply the prompt template to the whole dataset. Once this is done, we are then tokenizing the dataset that we have prepared here using this tokenize add label function. So you can see we have created this sample. So there is this input IDs, there is this attention mask, and the labels. So this message actually contains the result of the prompt that user is going to give, and the input ID is basically the prompt which we have received from the user. So once we run this cell, you can see it took around 26 seconds to do the dataset processing. And by the way, we are using NVIDIA's A100 GPU. So if we just do NVIDIA SMI, so we can see we are using A100 NVIDIA GPU, which has 80 gigs of VRAM. Coming back to our notebook, so here we are setting up the training configuration. So here we can see create pep config as one of the function. And you can see we have defined, so when we are doing pre-training, when we are doing fine-tuning, we are using LoRa based technique to fine-tune the Llama model. So if you want to know about what is PEFT training, so PEFT is parameter efficient fine-tuning process, which is used to transfer learning efficiently from the pre-trained model without modifying most of the original parameters. So basically what it does, for the pre-trained model which we have, it does not modify all the original parameters, so that we can efficiently train the new model and get the output. So there are different ways. So one of the ways LoRa, which is low rank adaptation. Okay, so moving forward, so here we are setting up the model, and we can call this create pef config to get this model in pef config as we have done here. And then we are specifying the training arguments. So one of it is output directory, where we are getting all the logs and everything. There are number of epochs, how many epochs we want to run the training for. And there are these other steps or the configs that are required for the training. And then we define this trainer, where we give this model the training arguments that we have created, the trained dataset, which contains 18K rows, but it has been tokenized after the dataset setup process. Okay, so once we have defined our training configurations, so we can also see what is our torch version. And then we have started the training process using trainer.train. Now, when we did use the A100 GPU, which has 80 gigs of memory, it only used around 11.6 gigs of VRAM, and it took around 1 hour 47 minutes for the training to be completed on this GPU. So here also we can see we are getting some training logs, and we can see the time it took to complete the training process. So once the training is done, we are now going to do an inference. So for inference, we are giving this prompt: create a Python class with the following attributes: first name, last name, and the address. And we are using the model for the generation part. So using this model eval, and so there is this function, this model.generate. Here we are actually generating the output, and then we are decoding the output. Because the model would be generating the tokenized output, we need to decode it before printing out the output. It took around 11 seconds, as we see here, to inference, for the inference, and this is the output which the model is able to create just giving this kind of prompt. So after fine-tuning, we can see how model is able to accept a prompt in terms of instruction and is able to generate the code that is required. And when it was not fine-tuned, it was in pre-trained mode, it was able to just do the code completion and was not able to follow any instruction. So that is the change that we can see after fine-tuning the CodeLlama model. So after that, we are going to log in into the Hugging Face to upload the model. Here you can specify your own token, which I have hidden for now. And then using this push to hub command, we can load the model and the tokenizer to the Hugging Face. So we can also go to our WANDB. So these are the logs and the configurations that were pushed to WANDB while we were training. So we can see different parameters here. We can also see what kind of GPU we have, the OS configuration, the Python version, and other things. And also all the configurations that were used for training the model. And also here we see some of the summary of the metrics, which includes the number of epochs, learning rate, loss, and so on. Yeah, so here are some different metrics, so learning rate, training loss, and all. And here we see the metrics of the system: process, GPU time spent, accessing memory, disk utilization, and the other details. Here we see the other system related details in form of metrics. These are some of the logs which are again generated by our script. Yeah, so this was about the logs which are uploaded to the WANDB. We can also go to the Hugging Face to see how our model got uploaded. So as you can see, once we have like fine-tuned our model, it is also being uploaded to the Hugging Face. So here we can see the different parameters which were there when we were fine-tuning our model. And in this files and version, we can see different files along with the model, adapter model that we have fine-tuned. So this adapter model can be like attached with the original pre-trained model to generate an output. So that is how we are like saving the major processing time and the resources required to train any big LLM model. So yes, so that was it about like how you can also train your own code generating LLM model using any of your dataset. This particularly was for Alpaca 20K dataset, but you can also replace any other dataset of your choice to fine tune the model and generate the code output according to your own choices. I'll also leave the GitHub link of this repository in the description of this YouTube video. Thanks for watching.